heat transfer mechanisms. First, conduction, which is a two reservoir, hot reservoir at temperature TH, cold reservoir at temperature TC. Between them, we have a slab of a material. This K depends on material. The thickness air, the cross area is A. The TH is less than TC. We see the heat transmit from this side to this side, pass through the slate at unit time as P conductor, is Q over T. It depends on the material, K, and the cross area, A. Definitely, the larger A, the larger Q, right? Also, it depends proportional to temperature difference, TH minus TC, and inversely proportional to its thickness L. We move K to down. You can rewrite it as ATH minus T hot R, where R equal to air over, we get a called the thermal resistance. Here, K is the thermal conductivity of the material. Okay? A is the cross-section area. Okay? L is the thickness of the sample slab. TH is the temperature of the hot reservoir. TC is the temperature of the cold reservoir. And R we call thermal resistance. The higher the R, the lower the K. There's poor conductivity and a good thermal isolator. This is some thermal conductivity. We will see water, glass is about 0.1, and the silver is very, very good conductivity, heat conductivity. Okay. Conduction through a composite slab. Here we have two slabs instead of one. This is K1, K2, L1, L2, the same cross area A, and the temperature between the contacts is Tx. We don't know. Okay, this is a hot reservoir at Th. This is a cold reservoir at Tc. When this is a standing state process, very standing, then we know that the heat passed through this slab 1 equal to the heat past slab 2 because they are standing. Okay, so in this case we see that we write it. The P, the heat conductor passes through 2. It can write K2A TH minus Tx over L2 equal to K1A. Okay, this is just Tx minus Tc over L1. This is physics. When in a state process, the heat passing through 2 is equal to heat passing through 1. From this equation, I can find Tx, the temperature on the between them. Okay. Once we find the Tx, we put it back, we can find the P. These are junior high school mathematics, so I'm not going to do it. We just get the answer. Look at this answer. We know L over K, we call it R. This is R1, this is R2. So this one, that heat conducted through this slab is A TH by TC sigma R. Instead of R, we have a sigma R. So that's very interesting. If you have 3, we get a 3. R1, R2, R3. If you have 1, we get R1. This formula is exactly the same as the previous one. This R called is a property attributed to a slab of a special thickness, not a material, because same material, different thickness, K will be different. Okay. The second way is convention. Okay. When you look at the flame of a candle or a match, you are watching thermal energy being transferred upward by convention. Such heat transfer occurs when flow, such as air or water, is contact with an object whose temperature is higher than that of the fluid. Convection is a part of many natural processes. Atmospheric convection plays a fundamental role in determining global climate patterns and daily weather variations. Glider pilots and birds alike seek rising thermals, a current of warm air that keeps them aloft. Huge energy transfers take place within the oceans by the same process. The third way is the radiation. The third method of heat transfer between an object and its environment is via electromagnetic waves. Visible light is one kind of an electromagnetic wave. Heat transferred in this way is often called thermal radiation, the heat. The rate P radiation at which an object emits energy via electromagnetic radiation depends on the object's surface area A and the temperature T of that area in Kelvin, and is given by P radiation of the object is sigma epsilon A T to the fourth, where sigma is a constant, we call it Boltzmann constant, and epsilon we call E, we call it represent the emissivity of the object's surface between 0 and 1. 1 in the maximum, the black color. The rate P absorbed at which an object absorbs energy via thermal radiation from its environment, which we take be a uniform temperature T environment, is P absorbed equal to similar sigma E A T to 4. Instead, the T of the body, we can T environment. So, an idealized black body radiator with epsilon equal to 1 will absorb all the radiated energy it intercepts. This is the one. So heat color blocks will absorb heat strongly, okay, and emit heat strongly too. Okay. Then the net rate P net of energy exchange due to the thermal radiation is P net equal to P absorbed minus P radiated. So it's sigma epsilon A T environment force minus T to the fourth. Sample. The figure shows a cross-section of a wall made of white pie of thickness LA. This is one. The white pie, thickness LA. And the bricks of thickness LD. LD is equal to 2 LA. This is double this LA. Sandwich two layers of unknown material with identical thickness and thermal conductivity. You have two same thickness. I don't know what material, okay? But their conductivity are the same, thickness are the same. The thermal conductivity of the pine is Ka, and that of the block is Kd. Kd equal to 5.0 Ka. So much easier to transfer heat. The face area A of the wall is unknown, but they are the same. Thermal conductivity through the wall has reached steady state. So this is steady state. The heat passes through this, passes through this, passes through this, passes through this. At the same time, it's the same. Okay, steady state. The only known interface temperature as T1 we know, 25 degrees. T2, 20 degrees. Okay, T2, 20 degrees. T5, minus 10 degrees. What do I want to find? What is the temperature T4? And we look this one, we know T1, T2. Okay, so the pass A, the energy pass A is Ka, area A, T2 minus T1, T1 minus T2 with area A. Okay, and PD is Kd, same A, T4 minus T5 over the D. In a state of a stating way, they are the same. Okay, we know there's T1, T2, we know LA, we know LD, we know KD, KC, T4. So we can from these three equations, we can find T4. T4 equal to Ka LD T1 minus T2 over KD LA plus T5. And then we know that LD is 2LA and KD is 5LA. So we put this number inside, okay, we get the T4 equal to minus 8.0 degree of Celsius. These are junior high school maths, so I'm not getting into the detail. It's very easy, okay. The key point is this point. This is a physics part.